This video is on section 7.5 notes, powers and roots of complex numbers. So this section is on de Moivre's theorem. This is a French name, and because of the order of the letters in there, it's a little bit hard for Americans to pronounce. So what I remember from college is my professor saying de Moivre, but when I looked it up to make sure I was saying it right, that was not correct. So de Moivre or de Moivre seems to be a little bit more accurate, but if you get somewhere close to that, I'll allow it. So the theorem is what we're going to cover first. And I'm just going to kind of lead you into it so it will make sense. So if we have z is our complex number, and it is r times cos theta plus I sine theta, and remember r is the modulus, and theta is the argument. Then if we wanted to know z squared, if we wanted to know z times z, then we would just have the modulus times the modulus. Z squared is r times r, and then it would be cos of theta plus I sine theta plus theta. So if you remember, when you have complex numbers in that trig form, the modulus in the front, when you multiply them, the modulus in the front would multiply for each of the trig numbers, the complex numbers in trig form, and then you add the arguments together. So z squared would give you r squared times cos 2 theta plus I sine 2 theta. All right, if we had this as z squared, then if we wanted z to the third, we would do z squared multiplied by z. And so z to the third would be the modulus of z squared multiplied by the modulus of z. So that would be r squared times r cos, and then the argument of z squared plus the argument of z. So 2 theta plus theta. And then same thing for sine, 2 theta plus theta. And so for z cubed, we would have r to the third cos 3 theta plus I sine 3 theta. And you can probably already see the pattern, but we're going to do it one more time. So if that's z to the third, what would z to the fourth be? For z to the fourth, you would have the modulus of z to the third, which is r to the third, times the modulus of z, which is just r, and then cos of the argument from z to the third, which is 3 theta, plus the argument from z, which is theta. And then we would do the same thing for sine. Oops. 3 theta plus theta. And so z to the fourth would be r to the fourth cos 4 theta plus I sine 4 theta. And so de Moivre's theorem is if you have z equals r cos theta plus I sine theta, if that's your complex number, and n is any positive integer, then if you want to raise your complex number to the nth power, it would be a modulus of r to the nth power plus cos n times theta plus I times sine of n times theta. And so you could see kind of how that was working here. Okay, so here we're going to go ahead and try this, but we're going to look at a very specific complex number here, and we're going to look at a complex number that is not in the trig form yet. So here's our complex number. The complex number is raised to the 8th power. So the first thing we're going to do is we're going to take that complex number and we're going to put it into trig form. And then after we have it in trig form, then we can use de Moivre's theorem and use this formula here. So I'm going to start off by taking the complex number and converting it into that trig form. So the modulus is the square root of a squared plus b squared. So square root 3 squared is just 3 plus 1 . So the modulus is 2. And then we have tan theta is 1 divided by root 3, 1 divided by root 3, which is the same as root 3 over 3. And if we can imagine graphing this complex number, it would be right root 3 up 1. This would be in quadrant 1. So I know that I'm looking for an angle that's in quadrant 1, where on the unit circle, the y-coordinate divided by the x-coordinate simplifies to become root 3 over 3. And that would be where the angle is pi over 6. Okay, so I now have my complex number figured out in the trig form. I know that the modulus is 2. I know that the angle is pi over 6. And so now I can go ahead and figure out what this complex number is raised to the 8th power. So z to the 8th power would be r to the 8th power cos 8 times theta plus I sine 8 times theta. Okay, so 2 to the 8th power, 256 cos, and then 8 over 6 can be reduced. That would be 4/3. So this is 4 pi thirds plus I sine 4 pi thirds, right? And they said to write the answer in the form a plus bi. So if they said to write the answer in the trig form, we'd be done, but we need to write it in a plus bi. And so we'll go ahead and distribute the 256 and simplify. So cos of 4 pi thirds is negative 1/2. Sine of 4 pi thirds is root 3 over 2, negative root 3 over 2. So half of 256, 128. So this is negative 128. And then 256 divided by 2 is 128 again. So negative 128 root 3. And the I is always going to go in front of the square root. So 128 I square root 3. There's our complex number written in the a plus bi form. All right, so here we had an example of raising a complex number to the nth power. On the next page, we're actually going to see how you can take the nth root of a complex number, so how you could undo that. If you have a complex number raised to the nth power, how could you undo that nth power to get back to a complex number? So we have a formula for this one as well. It's also based on the trig form. So you can see that from the complex number, you would calculate the modulus, and then you would raise it to 1 over n. So if you're trying to take the 5th root, you would raise it to the 1/5. If you're trying to take the square root, you would raise it to the 1/2, that sort of thing. And then over here, you can also plug the numbers in here to find these. So we're going to go ahead and try this. It says find all fourth roots of the complex number -8 plus 8i square root 3. So the first thing we're going to do is convert this into that trig form. So I'm going to find the modulus first. R equals the square root of -8 squared plus 8 square root 3 squared no, that's a big number, so I'm just going to do it all at once. So 64 plus 64 times 3 is just a larger number. So this is the square root of 256. I believe that square root is 16. Yep. Okay. So the modulus is 16. And then we would want to figure out what the angle is. So tan theta is going to be 8 root 3 divided by -8. So if we were to graph this complex number, we would go left 8 and up 8 root 3. And if we go left and up, that would be the second quadrant. This is in quadrant 2. So I'm imagining the unit circle. I'm picturing where in quadrant 2 is there a y coordinate divided by an x coordinate that simplifies to -√3, and that would be at 2 pi thirds. So theta is 2 pi thirds. Okay, so I'm going to go ahead and start plugging the numbers into this formula here. So I'm going to have the complex number is 16, and the root that we're trying to find is the fourth root, so 16 to the 1/4 cos, and then it would be 2 pi thirds plus 2 pi k. And this 2 pi k right here is just saying I'm finding all the coterminal numbers to that angle right there that I'm using. So 2 pi thirds plus 2 pi k divided by the fourth root, so divided by 4, plus I sine 2 pi thirds plus 2 pi k. I'm going to write this note over here. I don't want to lose it completely since these are my notes. Okay, so here's my complex number. And then I'll go ahead and simplify this. So 16 to the 1/4, or the fourth root of 16 is just 2. And then 2 pi thirds divided by 4 would be 2 pi twelfths. And 2 pi twelfths is just pi over 6. So this is pi over 6 plus 2 pi k divided by 4 would be 2 over 4. That's pi halves. So plus pi halves k. Okay. And so for me to be able to find all the different variations of this, to find all my complex numbers that are the roots of this, I just have to simplify this, really. So I'm going to distribute the 2. So I'm going to have 2 cos pi 6 plus pi halves k plus I sine, 2 sine pi 6 plus pi halves k, put I on the end, and I'm going to think about the numbers that are going to go in here for my angle are going to be pi 6 for the first one. So theta is going to equal pi 6. And then I'm just going to keep adding pi halves. So 1/6. I'm going to make this a fraction. Okay, and then I'm going to add 1/2. Okay, so 2 pi thirds is the next one. 7 pi sixths is the next one. 5 pi thirds is the next one. 13 pi sixths is the next one. And this is where I'm going to stop, because pi sixths and 13 pi sixths are actually the same, because 13 pi sixths is coterminal. It's exactly 2 pi more than pi sixths. So I'm going to stop here. This is coterminal with pi 6. So that's going to tell me to stop. And so these are where all of my answers are going to come from. Okay, so I'm going to go ahead and show my work for all of my answers. My first one is going to be 2 cos pi 6 plus 2 sine pi 6i. That's my first one. My next one would be 2 cos 2 pi thirds plus 2 sine 2 pi thirds I, and then 2 cos 7 pi 6 plus 2 sine 7 pi 6 I, and then 2 cos 5 pi thirds plus 2 sine 5 pi thirds I. So there's going to be 4 answers here that give me 4 different complex numbers. So I'm going to go ahead and start writing them out. And I'm going to write them in the a plus bi form. And I'm going to write them in that form just because the problem was given to me in that form. And it's typically, unless they give you a different explanation, it's most proper to match the form of the original problem. All right, so here's my first one. 2 cos pi 6 plus 2 sine pi 6i. Cos of pi 6 is root 3 over 2. So if I have 2 times root 3 over 2, and 2 times sine of pi 6 would be 1/2. This would be, cancel the 2's, root 3. Cancel the 2's, that'd be 1. So root 3 plus I. So there's my first fourth root of this complex number. My next fourth root, I'm going to go up here and show my work next. 2 cos 2 pi thirds plus 2 sine 2 pi thirds I. So cos of 2 pi thirds is negative 1/2. Sine of 2 pi thirds is root 3 over 2. So we have negative 1 plus I root 3. There's my second complex number. For my third complex number, I would have 2 cos 7 pi over 6 plus 2 sine 7 pi over 6. So that's 2 cos 7 pi over 6 is negative root 3 over 2. Sine 7 pi over 6 is negative 1/2. Negative root 3 minus I. So there's a pattern here. You can see we're getting all the different variations of this. You can probably maybe guess what our next answer is, but I'm going to go ahead and show my work. 2 cos 5 pi thirds plus 2 sine 5 pi thirds. Cos of 5 pi thirds is positive 1/2, so 2 times positive 1 would be 1. 2 times positive 1/2 would be 1. Sine 5 pi thirds is negative root 3 over 2, so 2 times negative root 3 over 2 would be negative root 3. So that would be minus I root 3. All right, now a calculator is not really going to be able to help you do this work. You can see a lot of this work we're using the unit circle. A lot of this is by hand. Our calculator doesn't give us those square root answers. However, you can use a calculator to check these answers. So if I wanted to make sure that this was the fourth root of this complex number up here, then I should be able to take this number and multiply it by itself 4 times and get back to that original complex number. So if I do square root 3 plus, and then the I is right down here, here's your imaginary number, plus I, and raise this to the 4th power, I get -8 plus this number I, and if I just double check to make sure that that's -8 plus AI square root 3, which was the original problem, you can see, yep, it was. So I can check my answers and make sure they're right, even if the calculator is not going to get the answers for me. Okay, so that's one way we can find the root of a complex number. This is a different asking of the problem, but the process is very, very similar. So it says find all complex solutions of x to the third minus 27. And this is a problem that we could have done earlier on in math. We just would have had to do it a different way. So x to the third minus 27, we can solve by factoring. We would factor it using the difference of cubes, which has a special formula. And when we find the difference of cubes, we get a real answer. And then we would end up with a quadratic that usually has complex solutions. And then with that quadratic, we would do the quadratic formula, and then we would get our complex solutions. So this is another way of solving that same problem where we wouldn't use the quadratic formula. Instead, we would use this formula that's kind of based on de Moivre's theorem. So just kind of a cool way of math tying together and having multiple ways of doing things. So the first thing we're going to do is we're going to set this up and plug the numbers into that formula. So first, if I was to find the real solutions for this by hand without factoring, I could just add 27 over to the other side, and then I would get x to the third is 27. And then I would cube root both sides, and I would end up with x equals 3. So if I think of this as a complex number, this would be 3 plus 0i. I can still think of it as a complex number. And I'm going to go ahead and just sketch a little graph of that complex number. If I have 3 plus 0i, if I have 3 plus 0i and I graph that, then I'd be going right 3. I wouldn't go up at all. I would just go right 3 and I would graph it this way. And it'd be a point that was on the real axis because the imaginary coordinate is just 0. So I would say for this that I have my modulus would be 27 to the 1/3 power. That's how I found the 3, is I took the third root of 27, and I would say that my argument, my angle, is just 0 degrees or 0 radians, because that's where I am over here. So I'm going to write that my complex number is 27 to the 1/3, because that's how I found this 3. I took the third root of 27, and I'm going to write cos of 0 plus 2 pi k over 3 plus I sine 0 plus 2 pi k over 3. And remember, the reason I have 0 here is because when I graphed it, I saw that I had 0 degrees or 0 radians is where I graphed that first real solution. Okay, so now I'm going to go ahead and I'm going to do the problem exactly the same way that I did the previous problem. So I'm going to say that 27 to the 1/3 is just 3. I'm going to have cos 0 plus 2 pi thirds Okay, so the arguments for my different complex solutions, I'm going to start with 0 for the first argument, and then I'm just going to go up by 2 pi thirds. So 2 pi thirds is going to be the second one. And then 4 pi thirds. So I'm going to just keep adding 2 pi thirds. The next one would be 6 pi thirds. And 6 pi thirds is just 2 pi. And I'm going to stop here because 2 pi is coterminal with 0. It's going to give me the exact same answer that 0 would give me. So I'm going to stop here because this is coterminal with 0. That's why I stopped there. That's how I know how many answers I need to have. So now to find my 3 complex solutions, I'm just going to plug in 0, plug in 2 pi thirds, plug in 4 pi thirds, and see what I have. So 3 cos 0 plus 3 sine 0i. There's my first one. Cos of 0 is 1. So I have 3 times 1. Sine of 0 is 0. So my first complex solution is 3. And we already have that one. That's the one that we graphed, right? So that's this one right here. Or you could say 3 plus 0i. So that's our real solution, okay? Our next solution, we have 3 cos 2 pi thirds plus 3 sine 2 pi thirds I. Cos of 2 pi thirds is -1/2. Sine of 2 pi thirds is √3/2. So this would be -3/2 plus 3√3/2. And I'll stick the I right up there. So if we had solved this problem using the quadratic formula, then we would write this all as one fraction. So from the quadratic formula, we would have had -3 plus 3i√3 all divided by 2. And then our last answer is going to be 3 cos 4 pi thirds plus 3 sine 4 pi thirds I. So cos of 4 pi thirds is -1/2 again. And then sine of 4 pi thirds is -√3/2. And so that makes sense, right? Because when you do the quadratic formula, you end up having -b and then plus or minus your square root. And so we keep our -b in the front. But in here, what was a plus in this complex solution is going to become a minus in this complex solution. So minus 3i√3 divided by 2. All right, so I just did the problem by factoring real quick so you guys could see the difference. So if I did difference of cubes, I would say x to the third minus 3 to the third, and then this is my formula for factoring difference of cubes. If you had me for Math 171, I always said this is same, opposite, always positive, so SOAP is how you remember to do the signs when you factored. And then this first factor is where you get your real answer from. Still a complex solution, but it's only got a real portion. And then over here, this quadratic that's left over, you always would have to use the quadratic formula to solve because it's not factorable. So here is me using the quadratic formula to solve this. And here I'm getting a negative underneath the square root. And so I'm pulling the negative out and putting an I. And then the square root of 27 is 3 square root of 3. So here's my solution. If I did the quadratic formula, you can see that I would have -3 plus 3i√3/2 and -3 minus 3i√3/2. So this is how we would have done it before if we were doing factoring in the quadratic formula. And then this is how we can do it strictly thinking of in terms of complex numbers and using formulas to do it. So same problem, 2 different ways of solving. But this is what we're looking at in the context of this unit.